everyone for coming. One thing I want to encourage everyone who comes to Girl Geek Dinner is to network.
Welcome to Xilinx. Our mission is to build the adaptable, intelligent world. We have some of the most brilliant people, and you will get to hear from some of them tonight.
Regardless of your background, whether it be software, hardware, or anything in between, we at Xilinx have a tool that will allow you to take your design and run it on our FPGAs easily and efficiently.
You can run different workloads at different times with the exact same piece of hardware.
Fewer DDR components are needed. For some extreme case, like this example,
the cost of doing ASIC is becoming prohibitive for many applications.
So essentially, video transcoding is the conversion of one video encoding format into another.
So machine learning applications are getting innovated at a rapid pace in every single industry segment, whether it is retail or finance or healthcare.
Performance and power both are advantage to integration, and that's where we think we're going in future.
Hello. Okay, here we go. Hi, thanks to you all for coming to Xilinx. My name is Angie, Chang, and I'm the founder of Girl Geek X. How many of you here, it's your first Girl Geek dinner? Okay, good amount. All right, so Girl Geek dinners have been happening up and down the San Francisco Bay Area for the last 10 years. About every week we're at a different company, and I'm really excited to be here tonight at Xilinx. Personally, I was really excited when I looked up the website, and I was like, I can't wait to come here, check out the technology, and the demos have been really awesome. I encourage you to hang out and look at them. And walking down that hall of patents was very inspiring, and of course the food was amazing. So thank you everyone for coming. One thing I want to encourage everyone who comes to Girl Geek Dinner is to network. And I know that's a kind of a scary term. We're always told to network, but one thing that I always try to do, even as an introvert, is to meet people, at least one or two people over dinner. When you guys are chewing your food, just talk to people, ask them what they're doing, if there's anything you can do for them, anything they can do for you. Just because people are often looking for new opportunities, they're looking to learn more about the technology, and also just to make friends. When you have friends in your workplace or in your industry, that's how we can stay intact. We all know that women are dropping out of the workforce over time, and that's really why we continue to do these dinners, is to encourage women to continue coming out, meeting each other, encouraging each other, and helping each other stay leaning in, or whatever you want to call it, to your career. So please enjoy yourselves, and thank you again, Xilinx, for hosting.
Wonderful. Thank you so much, Angie. So welcome to Xilinx. My name is Condron-Wells, and I am a senior manager in human resources. I have the pleasure of helping employees at Xilinx listen, give, and feel as though they belong. I'm a social scientist by background, and I grew up in this very specific niche of the semiconductor industry at another well-known company. Most of my career has been in this particular slice of the semiconductor industry, and I think in this moment, I just want to reflect on the fact that we have many things to be grateful for. And I want to start this evening with thanking a number of people. So first and foremost, thank you to the Girl Geek team for creating this type of forum for us to connect. So thank you so much, Girl Geek. Thank you to our Xilinx greeters, gurus, and guides. I hope that they're making your visit meaningful. If you haven't already seen other aspects of our campus, we welcome you to join us in the demo room later on. And first and of course, our guests, right? So you took time out of your day to come meet us. We know that you work hard, and we're all different types of Girl Geeks, right? But regardless of that difference, we're here together to celebrate that brilliance of who you are and share who we are. So thank you for taking time out of your busy days to join us. And speaking of Xilinx, how many of you knew what Xilinx is or does before you saw the Girl Geek invitation? Raise your hands. Wow, that's pretty impressive. You must be in fairly technical households. Because Xilinx, sometimes called Xlinx, but we help people understand how to pronounce it, isn't necessarily a household name. That said, we affect the lives of people every day as we're nested in technology that's used broadly around the world, affecting everyone's lives. Xilinx is a 35-year-old company founded, what I like to say, on friendship. It was founded on friendship and a very incredible idea that is continuing to create many innovations now and in the future. Our mission is to build the adaptable, intelligent world. We have 4,000 employees plus worldwide and 4,000 plus patents, giving us a 1-to-1 ratio of people to patents. When I articulate the pride I have in where I work and who I work with, I genuinely mean we have some of the most brilliant people in the world, and you will get to hear from some of them tonight. So we invented the field programmable gate array. Not something everyone hears every day, but this is a device that makes the life of an engineer easier. It speeds up their ability to perform their responsibilities and have chips work in various ways, right? Thousands of applications can be used. But these engineers are empowered to reprogram chips in the field in hours instead of waiting weeks to get a completely new product. So this is the power of what we were founded on, the concept of enablement, empowerment, and acceleration. We have over 60 industry firsts, and our latest product, Alveo, which is absolutely gorgeous and is in our demo room, you can see the board, is plugged into data centers, giving a 90x acceleration over a CPU. This nested technology is inside of thousands of products, changing the way we live, love, work, and play. We are not only diverse in our thought that creates this technology, we are seekers of innovation, and we welcome brilliant minds who want to play in this space as well. Tonight, our focus is on acceleration. You will gain insights into acceleration by the people who enable it. We will have 3 lightning talks, a panel, and Q&A, where we look forward to hearing your questions to dive a little deeper into this topic. After 8 p.m., we'll transition to dessert, for those of you who haven't already taken advantage of that. Some more demos just around the corner and some more networking. This is a very special evening for us, and we're thrilled to have you. Now on to acceleration. Let's let the lightning talks begin. May I have our first presenter? So please welcome one of our first of 3 presenters, Niyati Shah. Thank you so much, Niyati.
Good evening, everyone. So let me begin by introducing myself. My name is Niyati, and I work in the logic optimization group. I primarily focus on software architecture and algorithm design. Outside of work, I enjoy weightlifting and traveling, and doing what I love, both at work and outside, is what makes me a girl geek. So let me start by asking you all a question. How many of you here are hardware engineers? And how many are software engineers? Perfect. So as we can see right in this room, we have a range of distribution of engineers from hardware background and software background. And that, I believe, presents the direction in which Xilinx has been headed. Traditionally, Xilinx is a semiconductor and FPGA chip company, and most of our customers used to be hardware developers. But as we have moved into the data center and acceleration markets, more of our customers are coming from software backgrounds. And what I'd like to do today is give you an overview of the tools that we have that help our developers, regardless of their background, use our FPGAs to run their designs. So we have the hardware developers who code using RTL, Verilog, VHDL. And for them, we have our signature product, which is the Vivado Design Suite. Next, we have our hardware-aware system developers, software developers, who use C, C++, and System-C, and for them, we provide the Vivado HLS compiler. We also have our software application developers who tend to use FPGAs mostly for accelerating their products or their designs, and for them, we have the SDXL environment. And finally, for our data scientists who use frameworks such as Caffe and TensorFlow, we have the AI compilers or edge compilers. In the next few slides, I'm going to go into a little bit more detail onto each of these different tools so that you can get an idea of how they meet the needs of the targeted developers. So as I mentioned, most of our hardware engineers work with RTL, Verilog, VHDL. But the FPGA is a piece of hardware, and it's only going to understand binary numbers or bit stream. And so we have to take the RTL through a process to generate that bit stream. And the best analogy I can give is kind of a translator. So if you and your neighbor were to speak in, say, different languages, then the translator will go from your language and convert it to a language that your neighbor can understand. And so we take the RTL through a similar process. We start with synthesis. So there's the RTL, we apply synthesis, and the job of synthesis is to create a logical netlist, which is technology mapped to the targeted FPGA. Once that is complete, then we need to optimize the netlist, and that's where I come in. My team and I work on optimizing the logical netlist. We've optimized the design for power, area, timing, depending on the developer need. And finally, create an optimized netlist, which will better use the resources that are on the FPGA. Once that part is complete, we run placement. And the placement essentially takes these logical blocks here and puts them on physical locations on the FPGA. Finally, we have the router, which connects those physical blocks together. And after placement and routing are complete, we have a bit stream that we load onto the FPGA to run the design. Now, instead of starting in RTL, if our developers were to start, say, with C, C++, or System C, then an additional step gets added because we have to first convert those languages to RTL before they can be fed into the backend tools. And that's where our Vivado HLS compiler steps in. The HLS compiler provides an Eclipse ID and allows our customers to design and develop using our product. The Vivado HLS compiler can be thought of as sitting on top of the Vivado design suite. So once the C++ is converted into RTL, then we feed it into the Vivado design suite and generate a bit stream. And that allows us to provide a comprehensive solution for people starting with C++, or System C. Now, so far the tools I've talked about address the needs of our hardware developers. But for our software application developers, we also have a tool, which is our SDXL environment. The SDXL environment and compiler sits on top of the existing Vivado HLS compiler and the Vivado design suite, and allow users with no FPGA background, no hardware expertise, to take their designs and run them on our FPGAs. They also allow us to support heterogeneous applications. So most of our software application developers are trying to accelerate their designs using the FPGAs. And so the designs will have a software component and they will have a hardware component. And the best example I can give you is that of computer vision. So I'm sure some of you have security cameras at home. And in that case, you know that there are multiple parts to that. There is recording, live video, but there's also object detection, where it will tell you that your dog is running around or there is a robber in your house. And in that case, the object detection part is what gets accelerated using hardware. The SDXL environment provides multiple different tools to our customers. We have a debugger, profiler, libraries ranging all the way from low-level math libraries to high-performing DSP libraries. But the star of the show is the compiler. The compiler helps us provide a comprehensive solution for both the software parts and for the hardware parts. The compiler compiles the software part so that it can be ran on the x86 machine, and it compiles all the individual hardware components, the kernels, so that they can go onto the FPGA. The kernels are compiled using the XOCC compiler, which internally leverages the Vivado HLS compiler and the Vivado design suite to generate bit stream for the parts that need to be accelerated. So once the compilation is complete, then the software part will run on the host x86 machine, whereas the hardware part, which are the kernels, will run on the FPGA, and they will communicate with each other using our Xilinx runtime tools. Now, this SDXL environment and compilers are very crucial and critical building blocks in our next set of compilers, which are aimed towards our data scientists who provide us models in frameworks such as Caffe and TensorFlow. Our AI compilers, they tend to, the object here is to take the models that the customers have provided and optimize them with deep neural network pruning and quantization so that we can get optimized models. And these optimized models are then targeted using our SDXL compiler so that they can go into the FPGA and generate up a stream. Finally, we have our AI compilers, which provides for Python interfaces, and so we can integrate very easily with the Caffe and TensorFlow frameworks. What I would like to leave you with today is that regardless of your background, whether it be software, hardware, or anything in between, We at Xilinx have a tool that will allow you to take your design and run it on our FPGAs easily and efficiently. Thank you.
Thank you. Our next presenter is Changyi Su.
Thank you for the introduction. My name is Chang Su. I'm a design engineer from Device Power and Signal Integrity team. My job is focusing on memory interface timing analysis and live validation. So today I will go over one aspect of machine learning, the memory. So I will explain why memory is one of the enablers for machine learning and how Xilinx can be part of the solutions. Yeah, we know that deep learning is one of the many approaches of machine learning which try to simulate human brain working with neurons. The neural network has a layered structure. In each of the layers, the dot simulates a neuron. The line between the nodes is a weight. So all the neural network does is a computation to compute the output of each of the nodes by multiplying the weight and each of the input nodes, and then plug into the activation function. So as shown in this figure, compared to other machine learning algorithms, deep learning algorithms scale up much better with more data. Therefore, the performance of deep learning algorithm is limited by the need for a better hardware acceleration for scaling up data size and algorithm size. Recently, FPGA became a very strong competitor to GPUs to serve as a hardware-based accelerator for machine learning. So with a programmable, flexible hardware configuration, FPGA often provide better performance per watt to GPUs. Xilinx FPGA support many types of memory technologies, either internal or external to the device. Compared to the object memory, the on-chip memory has lower latency, lower power consumption, but higher data bandwidth. FPGA devices offer the industry-leading 500 megabit on-chip memory storage space. So this allows the users to create on-chip memory array of size to suit their applications, and also it limits some of the external components. However, the on-chip memory is very expensive and hard to expand capacity. Therefore, the hardware accelerators still have to depend on the external memory to meet the storage requirements from machine learning. And also, the bandwidth of the object memory is a bottleneck. So with Xilinx devices, engineers are able to optimize the memory solution for different applications. For example, for machine learning, the intermediate data with activation data is usually stored in the on-chip memory to reduce the data movement between the processor and the object memory. The HBM and DDR can be used to store the input data and write weights, the weight parameters. So when we're working on the memory solution, one big challenge is to trade off between the memory and the computer resources to achieve the best performance with the lowest latency and the lowest power consumption. So this is the most amazing part of my job in Xilinx, and this makes me a girl geek. As I mentioned in the previous slide, due to the capacity limitation on chip memory, hardware accelerators still have to rely on the external memory to provide the massive storage for machine learning. So over the years, the DRAM chip density keeps scaling up. Therefore, the DDR memory capacity upgrade is one of the easiest ways to immediately improve the system performance. So we can increase the memory density by using high-density DRAM chips or multiple die packaged DRAM chips. Also, the dual inline memory module, DIMM, is very effective to increase memory capacity with minimum PCB space. So also, DIMM is a module which contains several DRAM chips on one side or both sides of a small circuit board. DIMM can be also configured to a multiple RAM configuration to further increase memory capacity. However, with multiple loading, the signal integrity of the memory channel is severely degraded. So the entire system may not operate reliably at higher data rates. Fortunately, most of the case can be solved by optimizing the channel configuration with the experts, with the efforts and expertise from memory design system engineers. So over the past 10 years, the DDR memory data bandwidth capability did not evolve quickly enough to keep pace with the bandwidth demanding from applications such as machine learning, video transcoding. So to bridge the bandwidth gap, Xilinx introduced high bandwidth memory, HBM. HBM took advantage of silicon stacking technology to put FPGA and DRAM side by side in the same package. So this co-packaged DRAM structure, together with 1,000 data bit width, HBM not only can provide extra more storage space, but also enable terabit per second data bandwidth. So with HBM-enabled FPGA devices, fewer DDR components are needed. For some extreme case, like this example, without any external memory components, Xilinx HBM solution can provide the same capacity but much higher data bandwidth and better power efficiency. So the takeaway of my presentation today is evolving machine learning workloads demand very bandwidth requirements. Xilinx diverse memory technologies enable it. Thank you.
Thank you, Changyi. And our next speaker and final lightning talk presenter is Madhugiri Dayananda.
Hello, everyone. Today we're going to explore how video transcoding can be accelerated on FPGA in the context of data center. So, can you guys take a guess on what kind of video applications these are? Yeah, correct. Gaming. Sorry. Facebook. Yeah. Yeah, got it. So that's Facebook Live and Twitch live streaming. That's used for gaming. And it's just not these two applications. We also have YouTube Live, and LinkedIn just announced their live streaming application just a couple of weeks ago. And it's not just limited to these applications, and the live video is everywhere, and it's growing rapidly. What's happening behind these live videos? We have a heterogeneous distribution of clients, say, for example, our cell phones, the tablets, the PC, the TVs, connected over wired and wireless networks, and each of them have their own resolution and the network characteristics. And we want to deliver the live video to each of these clients. So, So to deliver the live video to each of these clients, the live video input is re-encoded with a better encoder at a different resolution and a bitrate, and using video transcoding. So essentially, video transcoding is the conversion of one video encoding format into another. What is the advantage of video transcoding? It provides savings in terms of bandwidth and the storage costs. So how many of you have seen live videos and you experience video stalls while watching live video? Yeah. So CPUs consume a lot of processing resources and power. And for live video applications, the latency is in the order of milliseconds. So here is a plot which shows the encoder quality preset versus the performance. And taking a specific example of X265 preset slow, it's the quality preset, and it's supposed to be very good, like when you look at it visually. So comparing that, if it's encoded with CPU, you get 10 frames per second, but if the same application is being run on FPGA, it's like 120 frames per second. And for data center context, it's not just the quality and performance, you also have to consider the power as well. So considering all the three into equation, you can see there is like 72x acceleration. how does the FPGA solution compare with the GPA solution? So here is an example of FPGA-based HEVC encoder compared against NVIDIA GPU hardened encoder. And we see at the same quality level, there's 35% bitrate savings, so which translates into your bandwidth and streaming cost reduction. Another reason for using FPGA for video transcoding. So the video codec world is changing with the introduction of new codecs every few years, and if you see the timeline there, from 2010 to 2020, we see four new codecs. We already have HEVC and VP9, and AV1 was just standardized last year, and VVC is going to be standardized next year. So if you have a hardened or a custom chip for each of these codec, if you have that, then it's going to be a lengthy design process, and also you can't reuse the hardware. So if you use FPGA, then the applications can be adapted. Say, on the same FPGA, you can have HEVC application being running, and also the VP9 application. So FPGAs are adaptable and reusable. What is happening behind the scenes? Like, how is the video transcoding happening on the FPGA? We have the live video coming in from the host CPU, and that's being decoded on the FPGA using H.264 decoder and scaled into multiple resolution using adaptive bitrate scaler. And these scaled resolution videos are again re-encoded with a better quality encoder and sent out back to the host. Here is this video transcoding stack that Xilinx offers. So I work end-to-end on this pipeline, building FFmpeg applications, XMA plugins, testing these applications on different SDXL boards, targeting different devices. And not just these, I also work on video algorithms, improving the quality, and benchmarking encoders from partners according to customer requirements. So I guess that makes me a girl geek. I work on things that I'm passionate about, video compression technologies. What I would like you to take away from this talk is FPGAs give you better performance, they are adaptable and reusable, and you don't necessarily have to be a hardware engineer to use FPGA. You can be a software engineer and still use FPGA to accelerate your application. Thank you.
Thank you so much, Uma, and to all of our lightning talk presenters. Let's shift gears to our panel of senior Xilinx leaders. Here to lead our panel discussion is Tom Wurtz, Senior Director of Documentation and Program Management, and our distinguished panel.
So tonight we're going to explore the topic of acceleration. We've got a great panel of senior Xilinx leaders here to join us in that discussion. So we're going to start with Jayashree Rangarajan. She's a Senior Director of Software Development, and her Girl Geek power is simplifying solutions to complex engineering ideas. We've also got Pouquette, who's our Vice President of Global Customer Operations, and her Girl Geek power is knowing what the customer knows, wants, and needs before they know what they want. Right? Next up is Jennifer Wong, and she's Vice President of FPGA Product Development, and her Girl Geek power is optimizing results for both engineering and management. And finally, we have Ambs Kesavan, who's Senior Director of Software Infrastructure Engineering and DevOps. And her Girl Geek power is improving the development efficiency of using tools both in the cloud and on-premise. All right, so let's talk about this acceleration. That's a pretty wide topic. We're going to take it in a couple of different directions. First, computational acceleration, and then we're going to make it a little bit more personal and talk about careers as well as teams. So we're going to start with the hard stuff. So we're going to geek out a little bit on computational acceleration. We heard Changyi talk earlier about machine learning. So this is things like image classification, motion detect, and speech recognition. So Ambs, I'm going to have you go first, and I'm going to have you talk us through some of the bottlenecks and challenges in that space.
Thanks, Tom. I actually view this as an opportunity rather than a challenge. So I'll talk about the opportunities here, and I'll explain why I view that way. So we are in an era of big data, and there is a lot of statistics about big data. And I was looking at some recent article, and that said every single second we generate about petabytes of data from connected devices and sensors around us. And 70% of this data is video. And that amounts to about 800 million hours every single day or something like that. And businesses are trying to take advantage of this data. They want to mine the data to be able to do two things. One is for better customer service and also improve predictability. So machine learning applications are getting innovated at a rapid pace in every single industry segment, whether it is retail or finance or healthcare. Uma talked about video transcoding, speech recognition, name it, every single industry is going through innovation. And these machine learning in applications, they actually have to use algorithms for actually doing the machine learning. And these algorithms, if you run on CPU, that is no longer sufficient. It is not scalable given the massive volume of data we are looking at. So acceleration is the way to go. And innovation needs to happen both in hardware as well as software in order to accelerate these machine learning applications and algorithms. And that's the opportunity, Tom. And Xilinx is well positioned to serve the needs.
Thanks. Laurie, maybe you can join in with a few more thoughts.
Sure, and I'll take this more from the practical application in the business. So we're building a lot of capabilities to accelerate machine learning, but we actually have to apply that too in our business. And in supply chain, there's quite a bit of opportunity in supply chain for applying machine learning to the business. And it provides good ROI to the business. A couple of the areas that we're looking at are what I call predictability or predictable analytics. And one of the applications would be being able to understand the profile of the die that's coming out of the fab very early on, so you can actually match that to the demand much earlier in the work stream and optimize the use of your materials. Another predictable application is actually in the back end. When you talk about equipment, one of the things that shuts us down is unplanned machine downtime. So if we can anticipate and understand the profiles of the machinery so that we prevent it from going down in the first place, it'll definitely propel the business. The challenges with all of this, though, are the massive amount of data that you have to gather to really train your models and make sure you have the right algorithms so you get the ROI out of it.
So there's clearly a lot of opportunity in this space. So you see companies like Google and Intel, they're doing these dedicated AI chips. There's dozens of startups that are actually going down this path as well. And maybe, Jayashree, you can walk us through kind of what you see in terms of where is the market going from here?
We all heard Ambs talk about petabytes of data getting generated. And there's also, she was mentioning about algorithms that need to be developed. And specifically, if you look at the computing today, CPUs generally are meant for general purpose computing. When you talk of AI and machine learning in particular, you have two types of learning. There is training and then there is inference, right? In training, you use all of this data that you have accumulated and you're training certain models to do a particular task, be it in whichever domain, whether it's retail or oil exploration or whatever. But then when you have to deploy that model actually for doing the inferencing, you want this to be done in such a way that the computation happens a lot faster and the CPUs are not scaling. You probably have heard in many conferences that Moore's law is not scaling anymore. So there is a need for us to be looking at how can we accelerate the solutions that are targeted for these specific applications. So now you're seeing companies looking for, like especially the examples that Tom, you gave about the GPUs, and that's primarily because they saw a need for how do I accelerate this? I can't do it just with software. I need to be building custom hardware. And it doesn't just stop with building that accelerator, but you need to have some surrounding support in the system because data that needs to come into the accelerator, how is the communication going to happen? So there is a need for these specialized architectures to be built, and that's why we are seeing a lot of these startups getting funded to find that next big accelerator architecture that you can build. And the second thing with machine learning also is you probably are hearing new networks getting created every day, right? So which means you want an architecture that you don't build for one network, but 2 years later you're not able to use it. So you want an hardware architecture that is scalable with the needs. And that's an area where the Xilinx provided solution, which is adaptable and reusable, you saw it in the presentations earlier, it provides solutions that people can use for building networks that can scale with new models that come in. And especially with the startups that you're talking about, I'm waiting to see as well which ones succeed, which ones get taken over.
Yeah, so adaptability and programmability, it's part of the Xilinx DNA. So when we think about programmability, there's the idea of buying a chip off the shelf and programming it to do what you want. But there's also the notion of once that chip is actually in operation, being able to turn off part of it and reprogram just that part to take on a different workload. And it's part of the kind of the general philosophy of Xilinx. And as we look forward to the next generation of chips, it becomes even more impressive what we're planning to do. So Jennifer, maybe you can walk us through what Versal looks like.
Earlier, I see a lot of hands go up when we ask who knows about Xilinx. So I saw a lot of hands go up. Then I heard how many people are hardware engineers here. So I do see quite a few hands go up. So I wouldn't be surprised that some of you here are some of our customers, or you have used our products in the past when you were in school. So you must be very familiar with our earlier product lines like UltraScale or UltraScale Plus. So Versal is a significant step up of UltraScale Plus in terms of performance. So what is Versal? Versal is our first 7-nanometer product, TSMC's latest process node, and is the industry's first ACAP. ACAP stands for Adaptive Compute Acceleration Platform. So this is truly a platform device, not your old FPGAs. So I should say this is the really revolutionary architecture. So this revolutionary architecture combines a scalar engine, an adaptive engine, an intelligent engine to give us the significant performance improvement. The performance improvement can go up to about 20x of today's GPU or 100x of today's CPUs. So now, how do we achieve this kind of a performance improvement? It's pretty impressive. So given today's topic, focus topic is machine learning and compute acceleration, I'm going to talk a little bit about the intelligent engine. Intelligent engine is also known as AI engine. Internally, we have a name called AI engine. So this is specially designed for compute-intensive applications like machine learning and wireless operations. So now go to the next level. What is AI engine made up of? It is really a wide array of integrated DSP engines, which are capable of floating point and complex MAC operations. Now we have all these very, very powerful engines. We need to think about how to connect them together in order to take advantage of them in terms of hardware acceleration. So if you have used of our products before, you must know like MPSoCs. So in MPSoCs, we have a processor subsystem sitting alongside with the FPGA fabric. And these two entities are sitting side by side with some interface in between them, but the bandwidth is relatively limited. So when they are operating fairly independently. So the difference between the older generation products and Versal is we added a very powerful NOC engine in between all these engines, powerful engines. NOC stands for Network on Chip. This is not new in the industry. So NOC is very standard in ASIC. But what we are doing here is applying it to our architecture in order for us to leverage the compute acceleration. So what is compute acceleration or hardware acceleration? It is what it is, a design when you can partition the area that are very, very performance critical. So you partition it out and put it into these powerful engines and use compute acceleration to make the performance improve. And then you can, after the partition, you can have the slower function continue to run on the processor subsystem, and that's how you achieve the big performance gain. And I'm going to stop right here. There are other innovations in Versal architecture. I'll be happy to talk to you if you're interested later this evening.
Thanks, Jennifer. So, I mean, Versal is definitely an example of technology escalating at an incredible pace. So I'm going to ask each of you to kind of give some thoughts on where you think the things are going to go in the next 3 to 5 years in the acceleration space.
Maybe I'll just follow up on what I just said. So today's product, what we have today, is pretty big. If you look at our die size, is huge, and power is pretty high. So they are going to data center, into the cloud, and I see this intensive computation not stopping, because this is in the very early stage, and I see that continue to go. But in 3 or 5 years, as our process becomes more mature, our technology become more advanced, I see more and more functions going to the edge devices, like mobile phones in your hands today. I think in future, that's where it will go.
So, Jennifer, let me add a slightly different viewpoint. We talked quite a bit about compute acceleration. Even in the presentations, we heard about compute acceleration. And here what happens is you're transferring massive amounts of data from storage to compute, doing the acceleration, and then transferring the results back to storage. And there is a lot of data movement happening back and forth. And that's not necessarily very efficient. You'll run into bottlenecks with storage and networking. And every single data center, whether it is cloud data center or on-prem data center, you're going to have compute, storage, and networking. So what if we do the computation closer to storage? So you're actually doing the acceleration closer to storage instead of doing the data transfer back and forth. And that's an area Xilinx is innovating. And that's one example that I can give is smart SSD announcement that happened a couple of months ago when Samsung had its tech day. And that precisely is doing acceleration at the storage itself. And there is also similar innovation happening on the networking with SmartNICs. So essentially, it's a converged solution with compute acceleration, storage acceleration, and networking acceleration. And that's where the industry, I think, will benefit a lot.
Maybe you could talk about the software a little bit, Jayashree.
So if you look at where a lot of this machine learning development is happening, it's happening on the cloud, and they are the software developers. If you saw in Niyati's presentation, data scientists are looking at this massive amounts of data, looking at how am I going to write the right algorithm to solve this problem, right? And they are operating at higher levels. So what I see happening with the software is many layers of libraries being built, where these are libraries probably optimized to work for the hardware architecture that you're targeting, not necessarily written by the data scientist, but it's provided by the company that's also delivering the hardware. Plus, there's probably going to be AI-specific library. Like, for instance, we talked about video transcoding. So if you have OpenCV libraries that need to be provided for you. So if you're a software developer, you understand this, right? Because we don't anymore write string compares and stuff. We use Boost libraries or STL. So you are going to see stacks of libraries built, which at the highest level, the application developer, whether they are in a CAFE framework or FFmpeg framework, if they're doing video transcoding, they're going to leverage these libraries. So I see a lot of innovations happening in that realm, and companies will be providing their own libraries. I see open source development of certain APIs that can be leveraged by people who are trying to address a lot of machine learning problems in various domains.
And then if you kind of take that from the engineering world to where is this all going to be used? Xilinx has long been serving multiple in-market segments, from automotive to communications, test and measurement, medical. But our new focus now is on the data center area, the proliferation of the data, the video. It's all going to be needing to be stored up in the cloud or on premises. So we've really now got this strong focus on data center. And as part of that, in addition to selling our semiconductor devices, we've also started to sell boards. So we have Alveo product, which you heard Eva talk about earlier. You can see it in the demo room. So this is now taking the acceleration capability from just the semiconductor to enabling the customer with a board. So they can use the board and then go on to their design work or their entire solution much faster. They don't even have to just start with the FPGA. Now, as we go out in time, what's going to be really good for everybody is we're still serving all these other end markets. And as end markets like automotive really get into advanced autonomous drive or advanced applications, they're all going to need to store that information somewhere. And they're all going to need to process that information. And they may need to do that at the edge very rapidly, or they may be able to do that in a central place. But basically what we're doing here with acceleration isn't just going to serve the base acceleration market, but all of our markets.
Well, we geeked out pretty hard there to the extent that we've pretty much used up most of our time. But I do want to take one moment to ask each of you, if you were to put into one single word, you know, what does it take to actually accelerate a team? What would that be? And let's start with you now.
Communication.
Teamwork for me.
Focus.
Tom, I'm going to go with 2 words. I would say it's the winning attitude.
All right, thank you very much to all of our panelists.
Thank you so much to our panelists and to our lightning talk presenters. At this time, we'd like to open it up to the floor, and I'll need to steal a microphone from one of our panelists, so we'll share. Pardon me, thank you. So you've heard a lot of different insights, different perspectives. We'd like to hear a few questions. We probably have time for, we'll take 3. So, and we'll continue the conversation afterwards. So if you're still burning, you have a burning question in your mind, please know that we are planning to be here until 9, and we have plenty of demos to share too. So, and don't forget to take your gift on your way out. I want to say that before you mentally leave. While I have your attention, that we have a gift for all of you that we would like you to take on your way out in the lobby of when you came in. So please be sure to take that with you. So that said, I've given you a little bit of time to think about your question, and I have a microphone right here. Come on up. Let's, if you don't mind saying your name and your question to our panel. Please.
Sarah Biabani, Great Chang, CTO. So question I have for engineering, we talked about acceleration. I've always thought of FPGAs as co-processors. They're part of this screen, right? They're not the star. They could be the star, right? They could be the diva. Right? So, so then there's the processor, right? And you're not going to get in the space of competing with x86 or ARM. So what does that architecture look like? What's your ideal architecture?
I think we have a pretty good, we do have a processor. So we have, so for the Versal, we have the A72 cores. We have a dual A72 core in the processor subsystem. In the scalar engine, what we call the scalar engine is the processor subsystem. Yeah, 2 A72 cores in there and then 2 R5 cores in there. So from a processing standpoint, we do have capability of doing that. And now we added a lot of these architecture that we can accelerate functions. So that is what we think our niche is. So we can partition it Where very critical functions, we can put it into the more expensive side. Like we use a lot of silicon area for acceleration hardware. So we would smartly do that and say, okay, what is the important one that we can partition out, put it into hardware acceleration, and leave the processor still running. So that is what we think we're the niche. Everything is on one piece of silicon. So think about it. If you are doing it outside, you have processors and other components. So the interface takes a very long time. The key is integration for us. Everywhere, the smaller the footprint, the more integration you do, the more performance both performance and power. So whenever you go off chip, power is a big deal. So performance and power both are advantage to integration. And that's where we think we're going in future.
Thank you, Jennifer. We have actually 3 questions just popped up right all in the same area. So we're going with that energy. And please, your name and your question.
Hi, I'm Savita. First of all, thank you to Xilinx for hosting this event. Given all the other Girl Geek dinners have been, it's nice to see somebody on the hardware chip design side kind of take a lead here. So my question is related to that, because most of the discussion in the big data enterprise SaaS or AI has been around the software and the algorithms. The first time I saw a focus on hardware was actually a startup grind where one of the presenters talked about, don't write off the chip guys yet, because there's a next revolution coming where you're going to see a lot of custom built chips for AI applications. And given that we're talking about, first of all, this is a Girl Geek dinner, and given that we're talking about the fact that we need women to be on an equal footing in the way the AI is going to evolve, what are some of the ideas you might have for some of the younger folks to continue in this space?
Mic check.
Hello, can you hear me okay? So I can think of a couple of things, right? Computer architecture, because as I was talking earlier about, hey, there's many architectures that need to be, they are probably waiting to be innovated, right? Because we are talking of machine learning in very many domains and stuff. So I do think as young women who are looking to, hey, what do I want to do if I want to enter into hardware? And I think having a good grounding in computer architecture principles is going to go a long way. And just learning the hardware aspect alone is not going to be sufficient. You also need to understand which domain you're targeting. So you need to know the end customer that you're going to be influencing. So you need to learn about the software component also. So I think if you want to excel in both sides, I think as you are getting your early education, having good grounding in both hardware principles as well as software programming principles help you better understand the needs on both sides. But as you go further and you're looking to specialize, then at that point it's your individual choice as to whether hardware attracts you more or software attracts you more. But I think it's good to keep your options open.
Great, thank you so much. One more question. We'll take 2 more questions and then continue with our networking.
Okay, my name is Wong. I'm a software engineer working in a hardware design company. So you already addressed a little bit about that. I just wonder if you can address a little bit more regarding to FPGA application in machine learning and hardware acceleration to win over ASIC in that field.
So I think the jury is still out, right? So I think everybody is working very hard. This is a very hot space. And I think everybody is trying a very different route. And Xilinx has Xilinx niche. And I think what we give here, or what our specialty is we are reconfigurable. aside from being able to partition, that's definitely a big deal. We can allow software to run on software, hardware, the fast fabric to run on fast hardware. The bigger part, I think, is the reconfiguring part, that which I didn't talk about earlier. So we talked about many, many different workloads today. During the day, the data center can be running one kind of workload. In the evening, is a different workload. So what we excel here is we allow reconfiguration. So even you can, within the ACAP, you can run different workloads at different times with this exact same piece of hardware. So we believe that it's a very big niche that we can further leverage in this particular space.
Thank you.
I just want to add that besides the reconfigurability, there's the costs. So the costs of doing ASIC is becoming prohibitive for many applications. So on higher volume applications, it's still an option. But many of our customers who might have classically done ASICs are moving away from it because it's just not making financial sense. So there's that piece of it too.
Thank you, Laurie. And our final question.
Hello, my name is Wolfgang. I'm a hardware engineer, and I want to thank you that I have a chance to ask a question, even though I'm not a girl geek. So my question is about reliability. When we have ultra high-speed computations in applications such as control of industrial processes or autonomous driving, it is not only imperative that those computations are very fast, but the results need to be very reliable. And we don't always have the option to just co-locate processor and memory, because we have a sensor somewhere, a camera that sends data to some processor, and that processor must make a decision and send it to some machine that needs to act and do the right thing. So what are your thoughts about reliability, or maybe a hint? It has to do with something with high-speed interfaces and robustness against bit errors, but there are also many other aspects to that.
Thank you.
Okay, so reliability has always been is a big issue for us. I mean, in the past, what we do is we allow 10-year reliability, and we do things very carefully with our foundry, because foundry give us some specs that we have to follow through. TSMC is pretty well known in terms of their being rather conservative. So they give us specs, and we always negotiate with them. There is a little bit of push you can do, because everybody's competing for performance and power. The more you can push the foundry, the more you can gain the advantage. So this is maybe against what you are asking, but what I'm trying to say here is we do a very fine balancing act in terms of performance versus reliability. We don't completely ignore reliability. We go for performance, but we always make sure that we can meet our reliability, and we do a very, very thorough quality QA in the end, and also we have qualification, pretty substantial qualification, in different times. Maybe you can add to it. Yes.
So on the quality side, we have many end markets we serve. So we have commercial grade, we have automotive grade, and we even have aerospace. So all of those have different levels of quality and reliability qualifications that we go through. So we definitely are very attuned to the upcoming challenges of the technology to be able to respond quickly in those types of situations you're describing. But we definitely offer a variety and do quite a bit of different qualifications depending on the markets that we're serving.
All right. Well, thank you all so much for your very thoughtful questions, and thank you all, our guests, our speakers, panelists, for your insights. We genuinely appreciate you taking the time to share your insights with this team and group. So that said, we are officially closing our technical talk, but we are not done with our evening yet, and we are happy to stick around and answer more questions. Some of our Xilinx employees are wearing Ask Me About stickers. You're welcome to engage with them. I will be wearing one too, so find me later. And of course, we have our dessert and networking and demos. So thank you all so much. This concludes the technical talk. Thank you.